Hello friends, today I am going to demonstrate a small concept in computer graphics, that is viewing in 3 dimension. Before that, we can see what's the use of normalized coordinates in computer graphics. We can see different display devices such as cathode ray tube, color CRT, LCD, LED, direct view storage tubes, plasma display, or in 3D display, or in vacuum fluorescent display. There are different screen sizes and resolutions, and all are measured in pixels. Pixel, in digital imaging, a pixel is also known as PEL or picture element, which is the smallest addressable element of a picture represented on the screen. We can see picture on a screen with a high resolution appears smaller in size, whereas the same picture on screen with a less resolution appears big in size. To avoid this mismatch, we make our program device independent. So, picture coordinates have to be represented in some other units other than pixels. These device independent units are called normalized device coordinates. Here we can see normalized device coordinates of 1 unit width and 1 unit length. Here it is represented as 0, 0 origin, and x coordinate is 1 unit, and y coordinate is here is 0. Here y coordinate is 0, x coordinate is 0 and y coordinate is 1. Then this is of 1, 1. There is 1 unit length and 1 unit width size. Interpreter is a system software. That one is used to convert normalized coordinates into device coordinates. For that, a simple linear formula is used. The formula is h equal to hn into hw, y is equal to yn into yw. Here x and y are actual device x coordinate and actual device y coordinate. Hn is represented as normalized x coordinate and yn is the normalized y coordinate. And hw is the width of actual screen in pixels, and yw is the height of the actual screen in pixels. And viewing transformation. An image is defined in a world coordinate system. That is what we are seeing in the nature. That is world coordinate system. That is always in Cartesian coordinate system. That is world coordinate system is application specific. For example, drawing dimensions may be meters, kilometers, feet or inches, etc. When picture is represented on display device, it is measured in physical device coordinate system corresponding to that display device. And a mapping of coordinates is achieved with the use of coordinate transformation. That is mapping the picture coordinate which is in the world coordinate system to display coordinate which is in the physical device coordinate system. Here in this example, this is a world coordinate system. The picture of the nature is represented here. It is infinite. That is, this picture is infinity. We cannot represent this as finite. Then we need this area only, this object or any object that where we want to display, that we have to select using this clipping window. That is, it defines what to display. Then this display information we are mapping to viewing coordinates. That is where we are going to display this one. That is viewport. That is, we are mapping this particular portion of the image to viewport. Others have to be clipped. Here we are representing this information as x coordinate is hw min and hw max. Thus window areas in between hw min and hw max. Y coordinate is also, this is in between yw min and yw maximum. And Viewport also, here also is represented as HV min and SV max. That is, if any point is here x, that s should be in between these coordinates. That is HV min less than or is equal to x less than or is equal to SV max. Then y coordinate YV min less than or is equal to y coordinate less than or is equal to YV max. Then only we are able to display that portion. To convert this one, there need to define a world window. Then we have to define a viewport also. Then compute a mapping from window to viewport. This figure shows mapping of object from window to viewport. Here we are representing a point in the WCS, that is represented by SW, YW, and we are mapping to viewport, and that point is represented here as SV, YV. That is in between, SV is in between SV min and SV max, YV is in between YV min and YV max. Same things also here, applicable here. To maintain relative replacement in viewport, as in window, we require this one, HV, that is coordinate in the viewport, HV minus HV min divided by SV max minus SV min, which is equal to SW, that is S coordinate in the WCS world coordinate system, SW minus SW min divided by SW max minus SW min. In the case of y coordinates also it's same, that is YV minus YV min divided by YV max minus YV min is equal to YW minus YW min divided by YW max minus YW min. Solving these two equations, then we will get SV, that is its coordinate in the viewport, which is equal to SV min plus SW minus SW min into some scaling factor. Then YV is equal to YV min plus YW minus YW min into scaling factor Y. We are represented here as scaling factor Y. That will be, that is SH is equal to SV max minus XV min divided by SW max minus SW min, and the scaling factor SY is YV max minus YV min divided by YW max minus YW min. That is represented here. We have selected this object is this one, and we have selected this window and translate to the origin and scale it. Here we are using the scaling factor below 1 less than 1, so it is smaller in size. Next thing, we have to translate the smaller size scaled one to the original position. And the workstation transformation is given by the equation W is equal to T into S into T inverse, where T is equal to matrix 1 0 0 0 1 0 minus XW min minus YW min 1, and the scaling factor S is equal to SS 0 0 0 SY 0 0 0 1, and T inverse is equal to 1 0 0 0 1 0 SW min YW min 1. And the 3D viewing transformation, here it is represented here. Construct a world coordinate seen from modeling coordinate transformation. That is, here it is in in that last example we have seen that picture of the nature, then that is in the world coordinate system, and convert that picture world coordinates system to viewing coordinates, then it will be in the viewing coordinates, and we have apply project transformation, and after that projection coordinates, then transform that projection coordinates to normalized coordinates, and that normalized coordinates map that normalized coordinate to device coordinates. Then what we will get the output in the device, output device is device coordinates, which is of 2 dimension. And the 3D coordinate system is represented here. Here is x this xy plane, and this is yz plane, and this is zx plane, x-axis, y-axis, z-axis, and a point A is represented here. The coordinates are A, x coordinate is A, y coordinate is B, z coordinate is C. Here it is A, x coordinate is A, y coordinate is B represented here, z coordinate is C is represented here. The point is A, B. A is of coordinates A, B, C, small a, B, C. And point and line representation, we have already seen that the point is represented by ABC or XYZ. And for line representation, we need 2 points, starting point, ending point. And starting point is represented by S1, Y1, Z1, and ending point is represented by S2, Y2, Z2. For the line equation, we can see that y minus y1 by s minus s1 is equal to y1 minus y2, y2 minus y1 by s2 minus s1, and z minus z1 by s minus s1 is equal to z2 minus z1 by s2 minus s1. Or we can see that x equal to s2 minus s1 into u plus x1, y is equal to y2 minus y1 into u plus y1, z is equal to z2 minus z1 into u plus z1. And plane is represented by the equation ax plus by plus cz plus d is equal to 0. Here a, b, c, d all are constants. Or we can see that divide by a, we can get x plus b1y plus c1z plus d1 is equal to 0. b1 is equal to b by a, c1 is equal to c by a, d1 is equal to d by a. If you know 3 points, we can determine the plane equations from this one. That is h1 plus b1 y1 plus c1 z1 plus d1 is equal to 0, h2 plus b1 y2 plus c1 z2 plus d1 is equal to 0, h3 plus b1 y3 plus c1 z3 plus d1 is equal to 0. Solving b1 c1 d1 yields a plane equation. Also, a plane can be specified as a single point plane, that is represented by a point in the plane, that is SP, YP, ZP, and the normal vector that is perpendicular to the plane. Nx, Ny, Nz is represent this one. Then plane equation can be Nx into S minus HP plus 1y into Y minus Yp plus Nz into Z minus Zp is equal to 0. And here are two geometrical transformations, that is perspective projection and parallel projection. Here, in the case of perspective projection, there is a center of projection here. Here AB's line is represented here, and A dash B dash is represented in the projection plane. Here this is a center of projection, it is always our eye. In the case of parallel projection, there is no center of projection. The center of projection, we can say that it is infinity. Then AB is represented here, projection plane of A dash B dash is represented here. Then in the case of parallel projection, suppose the direction of projection is given by the vector HP, YP, ZP, and image is to be projected on the XY plane. If we have point on the object at x1, y1, z1, then we wish to determine where the projected point x2, y2 will be. Then write in the equation passing x1, y, x, y, z, we can say that the direction of projection will be x equal to s1 plus spu, y is equal to y1 plus ypu, z is equal to z1 plus zpu. And where does this line intersect the xy plane? Since u is equal to minus z1 plus zp, substituting this one, s2 is equal to h1 minus z1 into sp by zp, also y2 will get. Then we can represent this in matrix form as S2 matrix H2 Y2 Z2 1 is equal to 1 0 0 minus SP by ZP, 0 1 0 minus YP by ZP, 0 0 1 0 0 0 0 1, the one diagonal representation into H1 Y1 Z1 P matrix. And in the case of perspective projection, the farther an object is from the viewer, the smaller it appears. If it is far, it will be smaller in the output view. If the center of projection is represented at HC, YC, ZC, and the point of object is H1, Y1, Z1, then projection ray will be represented as the equation H equal to HC plus S1 minus HC into U, Y is equal to YC plus Y1 minus YC into U, Z is equal to ZC plus Z1 minus ZC into U. And the projected point S2, Y2 will be the point where this line intersects the HY plane. For this intersection point, that is Z is equal to 0, we can compute U as minus HC by Z1 minus ZC. And substitute in this one, we will get S2 is equal to HC minus ZC into S1 minus HC by Z1 minus ZC. Y2 is equal to YC minus ZC into Y1 minus YC divided by Z1 minus ZC. Or we can represent it in the matrix form as matrix S2, Y2, Z2, 1 is equal to matrix minus ZC 0, 0, HC, 0, minus HC, 0, YC, 0, 0, minus 1, 0, 0, 0, 0. 0 0 1 minus HC into matrix S1 Y1 Z1 into 1 Z1 1. and the difference between this parallel projection and precipitated projection